Alright, so we're going to look at problem number 3 from the 2018 AP Chemistry Free Response section. In this video, we're only going to look at A through F. We'll do G through I in a separate video just because this is a very long problem. And so I'm going to break this up just a little bit here. So let's just jump right in. We are asked to answer the following questions related to iron and its two ions, Fe2 plus and Fe3 plus. And the first is just a simple question asking for us to write the ground state electron configuration of the Fe2 plus ion. So we would look at our periodic table, and electron configuration is the superscript method, and we would just start writing down what we read starting at the beginning at hydrogen until we reach iron. And then at the end, we'll pay attention to the fact that this is Fe2 plus. So we would just start at the beginning, and we would have 1s2, 2s2, 2p6, 3s2, 3p6. Now, here's where we have to start paying attention. If we were writing the neutral electron configuration of iron, it would be 3p6, 4s2, 3d6. And remember, transition metals are a little unusual. The first electrons they lose come from their S because they lose electrons from the highest occupied energy level first. We have electrons in the 4s, we have electrons in the 3d. The electrons in the 4s are lost first. So since this is 2 plus, there is no 4s2 right here. They are gone, but the 3d6 still remain. You also absolutely could have done the noble gas shortcut method of argon in brackets representing 1s2 through 3p6 and then just 3d6. And that was worth 1 point. So we were then given this table showing the ionic radius in picometers of Fe2 plus and Fe3 plus. We notice that Fe2 plus is larger. B, the radii of the ions are given using principles of atomic structure. Explain why the radius of the iron 2 plus ion is larger than that of the iron 3 plus. So as we've discussed in class, we need to compare these to each other. We need to see what do they have in common, what do they have different, and what is something that could affect atomic size. So they are both iron, so they're going to have the exact same number of protons. But 2 plus and 3 plus means the number of electrons will be different. Having only lost 2, iron 2 plus will have more electrons than iron 3 plus. So that is what we would use for our answer. They have the same number of protons, but Fe2 plus has a greater number of electrons than Fe3 plus. Fe2 plus will have more electron-electron repulsion and a larger radius. So same number of protons pulling the electrons in, but because Fe2 plus has more electrons, the repulsion in the outer electrons is greater, and that causes it to be bigger. And that was 1 plus. Just a 1 point question. C, iron 3 plus interacts more strongly with water molecules than iron 2 plus. Give one reason for this and justify your answer using Coulomb's law. So we automatically try to remind ourselves about Coulomb's law. So the force of attraction is our little Coulombic constant multiplied by the value of the two charges in coulombs divided by the distance between the charges squared. So the charge values have a direct relationship to the force of attraction, and the radius has an inverse relationship to the force of attraction based on where they are in our equation. Well, water is polar, and Fe3 plus and Fe2 plus are both polar, so they will have an interaction. Actually, it'll be a ion dipole interaction because this being an ion and then water being a dipole. So we want one reason for this stronger interaction. We have to relate it to Coulomb's law. Well, you have two choices. Fe3 plus has a bigger charge, and a bigger charge would result in a stronger force of attraction. Or, as shown in our little chart right here, Fe3 plus has a smaller radius, so it can snuggle up a little closer to the water because it's smaller, so the distance separating them will be smaller, and because it has an inverse relationship to the force of attraction, it means the force of attraction will be larger. So you could go with either of these. You would just want to explain a little bit more than I did here. I was just keeping this all on one sheet, but that would get you 1 point. We then change tact here. A through C, kind of their own little thing going on here. The rest, D through F, looks at a titration. So a student obtains a solution that contains an unknown concentration of Fe2+. To determine the concentration, the student titrates a sample of the solution with the permanganate ion, which converts iron 2+ to iron 3+, and we're given this equation right here. So this is an acidic solution, hence the H+ that we see. And this is an oxidation-reduction reaction taking place, and 5 moles of iron 2+ will react with 1 mole of permanganate, and in the end what results is 5 moles of the iron 3+ ion. We're first asked to write a balanced equation for the half reaction for the oxidation of Fe2+ to Fe3+. So if we were to break this into its half reactions, one half reaction would be the Fe2+ becoming Fe3+. The other half reaction would be MnO4 minus becoming Mn2+. And when we do each half reaction and combine, that's where the H+ and water come from. Not a lot of students like creating the whole here, but the half reactions are usually easier if we just remember our little steps. And we should actually be thankful we're asked to write the equation for by far the easiest of the two half reactions here. So we start with Fe2+, and we know we're going to become Fe3+, and the rules are, well, we balance everybody that's not H and O first. Well, 1 mole of iron, 1 mole of iron, that's balanced. There is no H+, there is no O- to have to worry about balancing here. So we just go straight to the end where we make sure that each side has the same overall charge. So I have Fe2+, Fe3+, overall positive 2, overall positive 3. I need to give 1 negative electron to the right, and now overall 2+, overall 2+. This is my balanced half reaction. It is the oxidation half reaction. As you can see, this electron is being lost, and this was worth 1 point. E, the student titrates a 10 milliliter sample of the Fe2+. So we pay attention that this is 10 milliliters. Calculate the molarity of it if it takes 17.48 milliliters of this molarity of potassium permanganate to reach the equivalence point. This is the net ionic equation here. The potassium would have been a spectator ion. That's why we do not see it here. That doesn't really matter. Just this molarity is 0.0350. So to reach the equivalence point, so we remember what that means. At the equivalence point, the moles of the Fe2+ and the moles of the MnO4- are present in the correct combination so that they completely react with each other. So when in doubt, we find the mole. So the first thing we would do is we would take our volume of potassium permanganate in liters, multiply by the molarity, and we would get the number of moles of potassium permanganate. And literally just doing that, which we all know we're supposed to do, we're supposed to find moles when we can, that got us 1 point. Notice, due to sig figs, that the 0.0350 was 3 sig figs. I wrote my answer with 3 sig figs for the number of moles of KMnO4. Continuing on, the balanced equation had it being 1 mole of permanganate to 5 moles of iron, because we're trying to solve for the molarity of the iron. to get the molarity of the iron, we need the moles of it divided by the liters, which we know. So we're kind of looking for the moles of iron as the main thing here. So due to the 1:5 ratio, we multiply by 5. We get 0.003059 moles of Fe2 plus. We just, to get our molarity, we divide by the volume in liters. It was 10 milliliters, so 0.01 liters. We divide, and we get 0.306 molar Fe2 plus for our answer. And that was 1 point for getting the correct value of the molarity. And to finish this video, we're going to end at question F. Explain why a 25 milliliter flask would be a poor choice for delivering the required volume of the Fe2 plus. So that's going to be a big problem here. It says you have the choice of 25 milliliter burette, 25 milliliter graduated cylinder, volumetric flask, and a beaker. So that's going to be a big problem. A 25 milliliter volumetric flask is only good for precisely measuring 25 milliliters. The beaker is not very precise. The graduated cylinder is better. It is more precise than a beaker. Remember, the skinnier glassware gets, generally you are more precise with your measurements with it. Well, the burette's the skinniest of them all. That would actually be the best to use to get the amount of Fe2 plus that we want. The volumetric flask would only be precise if we were getting 25 milliliters. So we just need a quick answer that a 25 milliliter volumetric flask is only to precisely make or dispose, I guess, is a little bit better their way to say it, to dispose of 25 milliliters. So that is A through F for question number 3 for the 2018 AP Chemistry free response.